Okay, hello everybody. Welcome to our seminar today. We are very happy to have a distinguished speaker with us, Manuela Temmer from Graz. So Manuela earned her PhD in astrophysics from the University of Graz 20 years ago and completed postdoctoral research fellowships at the Hvar Observatory of the University of Zagreb in Croatia and at the Space Research Institute of the Austrian Academy of Sciences. In 2014, she was a senior research fellow at the Lockheed Martin Solar and Astrophysics Laboratory in Palo Alto in California. We know Lockheed Martin has a very strong solar team, and I mean, they have been participating in most of the important solar missions. Since 2016, Manuela is an associate professor at the University of Graz, where she leads the heliospheric physics research group. And in 2022, she became the head of the Department for Astro and Geophysics at the Institute of Physics of the University of Graz in Austria. Her research focus lies in solar and heliospheric physics, with application to the impact of solar activity on Earth, as well as human and robotic explorers across the solar system. She works towards understanding the physics behind the dynamic processes and interrelationships between flares, coronal mass ejections, and solar wind structures in interplanetary space. And I hope that everybody will appreciate that we are going to learn some interesting things today about the heliosphere. So
I hope so.
Manuela, thank you very much for giving some time and for being with us here today, and the floor is yours.
Yeah, thanks, Janis, for the nice introduction. I will share. I think you should see now my presentation in full.
Yes, yes, we can see the slide. Yes,
yeah,
fine.
Perfect. Right, so I would like to kind of give you a bit of, information on the structured heliosphere. I hope, as Janis said, to learn something. And it's all about solar winds, transient disturbances, also, as we know, coronal mass ejections, to call them, and also their solar origin, because if we understand better how they or where they originate and from which sources they come from, we also can kind of model them in a more detailed way, and eventually also simulate and forecast those events which we are interested in. As we discussed just a few minutes earlier, I also wanted to highlight that was the aurora in Graz. Unfortunately, not observed by myself, but from my PhD student Florian Koller. He made this very nice movie, including also kind of these wavy structures that we are used to see only in the higher latitudes of Earth. And yeah, this most recent geomagnetic storm, which caused a KP of 9, was really something outstanding, which we saw only in cycle 23, because 24 was a weaker cycle. Yeah, this is all about. So how are these kind of phenomena that we see in very low latitudes, even in Southern Europe, in your place in Greece, how are these kind of formed? How do they interact with Earth? And besides having this beautiness of kind of effects, we also need, as a modern society, be prepared to be kind of have an impact on technology and for example, yeah, radiation and all that stuff. So setting the scene a little bit, what is it all about? So when we're looking at the source of these events and basically how the heliosphere is structured and why transient events occur, it's all about the magnetic field of the sun. The magnetic field is structuring interplanetary space, as it cannot remain in a static equilibrium due to the coronal temperatures of several million degrees. So this corona needs to be or needs to expand it continuously, and this is then resulting in an outflow, so-called solar wind. We see already in this cartoon to the left, which I borrowed from Janet Luhmann from a summer school presentation. The magnetic field consists of closed structures and open structures and combinations of those, so structures that dynamically open and close. In principle, these interplay between open and closed magnetic fields shapes our interplanetary space and also causes geomagnetic effects. The closed fields are the main sources of the so-called slow solar wind. Here we are in the 400 to 500 kilometer per second regime, and the open fields are the sources of the fast solar wind in the 600, 700, 800 kilometer per second regime. And the open fields are predominantly, or the main source are so-called coronal holes, so dark regions on the sun. When we have the interaction between these fast and slow flows, we form so-called stream interaction regions. And those coronal holes are rather long-living structures, so that also means they co-rotate with the sun, and then they are called co-rotating interaction regions. Magnetic reconnection, so a reconfiguration of the magnetic field, is basically the driver of coronal mass ejections and transient events. And this is the way to open field from closed field and closed loops that were previously open, so the change in this configuration. And this powers coronal mass ejections, so the field that closes down kind of expands and then gets ejected into interplanetary space. So the short-term changes as this reconnection, they happen in the lower corona. Is there some question or? Okay. I guess you can still hear me.
Yes, we can hear you.
Yes, okay.
Yes,
I just
yes.
heard some echo. Okay. So the short-term changes, reconnection, they happen in the corona, so these processes. Unfortunately, we cannot measure magnetic fields there, so that means we are basically relying on simulations there. And the photosphere, where we can measure magnetic field, and that kind of provides us the input for almost all our models, this kind of covers mostly the long-term changes. So if there is strong reconnection, you will not immediately see that in the photospheric level. So basically, models, they play a substantial role, not only in the magnetic fields determination, because we do not have observations, but also observational gaps because of the huge space that we need to cover. So when we start focusing or learning effects that start from the sun and try to kind of follow them from the sun to the Earth, we only have a few in situ measurements, usually spacecraft that orbit around planets, also further out around Mars, for example. So we can follow these events from sun to the inner heliosphere. We have in situ measurements, so probes that kind of give us detailed measurements on site, so plasma magnetic field parameters. And on the other hand, we have remote sensing image data that give us a larger field of view, but usually we are limited in the information that we derive from those. Bright and dark structures can be either temperature related or density related, so it's not easy to disentangle or derive parameters out of that. As you can see here, there is a fleet of spacecraft out there that gives us quite some good measurements, but still, due to the huge space that we need to cover, the observational gaps again need to be filled by models, which play the substantial role. And most important, or at least the kind of scientific missions here that give us brand new and unprecedented views on the heliosphere are Parker Solar Probe, having in situ and white light observations, and orbiter, including white light and UV observations in addition to the in situ observations. Talking about understanding solar activity and how they interact with Earth and other planets is space weather, so to say. So this solar terrestrial physics and the research that we do is a highly interdisciplinary field. So it's not only that we cover the sun side or the sun aspect, the solar aspect in solar physics, we need to understand how these structures, these events, when they eventually form and kind of propagate in interplanetary space or in the solar wind, how these interact with each other. So structures that interact with transient events. And in that respect, so heliospheric physics is kind of dealing with the processes that kind of determine the propagation of these of CMEs, for example. And last but not least, we need to understand how these events, how these incoming solar wind structures, either solar wind itself or CMEs, kind of interact with the geospace. And in that respect, the magnetosphere, ionosphere, thermosphere, but also we know that there are surface effects like ground-induced currents that we observe. This is also from a same PhD students that observed the aurora. A very nice cartoon showing a CME with its shock and sheath structure and how it changes. Also, you see field line draping here and how that then interacts with the magnetosheath and magnetosphere of Earth. And in that respect causes, for example, magnetosheath jets, which is a very young field, even for the magnetospheric people. But they are supposed also to kind of generate space weather effects and kind of putting together different disciplines and learning from each other and kind of disentangling also universal processes and exchanging information about how to investigate data. So it's a big plus currently so to go for interdisciplinary research. Flares, CMEs, as already mentioned, magnetic reconnection. So the reconfiguration of the magnetic field is their common ground. And with that, we power CMEs. So we kind of reconfigure the field such that that the structure starts to expand. And we also release a lot of free magnetic energy. And this free magnetic energy, it leads to particle acceleration, it leads to heating, waves, and all that is then seen on the surface of the sun. In SDO AIA, in the different wavelength ranges, so starting from the photospheric level, UV, chromosphere, so lower corona and chromosphere, and these are the hotter channels, we very nicely see how these energy release looks like. So these flares that are generated, they are bright, sudden bright enhancements. And so we newly connect the different magnetic field topologies and change with that also the magnetic pressure. And in that respect, also waves can occur that propagate over the surface. In cartoons that already were established in the mid of 90s or even earlier. So we see also the connection between those so flares and CMEs, so the upper part of this reconnection point and the lower part with the different kind of surface structures that are then observed. And in a more modern three-dimensional view, we also see here how the structures, how these closed loops, they kind of connect, build an arc, build a new type of loop down there, and in that respect then accelerate particles and kind of lead to this brightening and also particle acceleration. In that respect, so flare, CME, SCPs, so solar energetic particles, how they relate to each other. What I show you here is basically an idealized picture, an idealized story. If there are complex events or complex processes ongoing, you will not find a very kind of, you cannot disentangle very nicely between kind of different events or brightenings. But usually if you have, I mean, as said, in an idealized story, you start having a so-called a pre-flare phase where sometimes already a thermal emission, so some brightening can be observed in the remote sensing image data. In H alpha, usually kernels start to bright up. Those are already presumed to be the kind of the foot point connections along which the particles kind of are accelerated downwards and interact with a denser chromosphere. Usually this pre-flare phase is also related to a short or a kind of a weak or a soft rising of the filament itself before it finally starts to erupt. This is followed then with a flare onset or the impulsive flare phase. We also see in the different wavelength ranges the profiles when the brightening starts so to enhance in the intensity. It happens so the peak or this rise phase is a little bit different depending on the wavelength range. So this usually relates to particle acceleration and heating. So the acceleration of the particle is usually related to hard X-rays and gamma rays, so the very high energetic kind of signals that we get. They start to occur earlier in comparison to H-alpha. That is kind of relating us to lower energetic kind of signatures, heating that occurs then later on. So also investigating the time differences between different wavelength regime and when they peak is also giving us an information about the reconnection process and particle acceleration process. With the flare onset, usually also the CME body forms. So we kind of close magnetic fields and come from so enhance the poloidal flux, and in that the CME starts to erupt. And also solar energetic particles are accelerated during that phase. In the decay phase, usually then all the wavelength ranges or the signatures, they go then back to the pre-flare level. Solar energetic particles are usually then protons mainly, and can also then get detected on the surface of a planet like on Earth. GLEs, for example, are the most energetic ones, ground level enhancements. So these are most energetic and are usually then related also to the most strong flare brightenings and also CMEs. So there's also a review by Olga Malandraki and Norma Crosby, and the connection to the CMEs is given in a review by Zhizhan. If you're not familiar with flare classification, so a very brief overview. So we already talked about soft X-ray and H-alpha. H-alpha was earlier because H-alpha started in the 40s to become a very kind of popular wavelength range. Ground-based observatories could do these observations very easily, whereas soft X-ray needs satellite missions to kind of be able to observe these wavelength regime. And so there's usually importance classes that are defined in H-alpha together with an area, and the soft X-ray classes are usually then related to the GOES measurements by the GOES satellite. And all together, so it's basically it's a temperature and emission measure, so a combination of thermal and kind of so non-thermal and thermal plasma that gives us that information. And soft X-ray and H-alpha, as already said, is usually only related to the thermal emission. In that respect, we also need to be careful about profiles. As said, different wavelength can give us a little bit different information. Moreover, soft X-ray classification is an integrated intensity over the entire visible disk. So it also does not give us spatial information, while in H-alpha you usually see the brightening at a specific location, and usually that is then related. So that area relates to a specific flare and intensity. Most powerful eruptions are usually associated with powerful flares. So there is a so-called flare CME feedback relation. It's basically, as already shown in this cartoon, we have a reconnection point or a current sheet where reconnection is happening. We have in the upper part the erupting flux rope, in the lower part then the flare, together with the different emissions that are measured. Depending on how efficient this reconnection process is, so how fastly I can kind of reconnect or reconfigure the magnetic fields. It all depends also on the magnetic field strength, of course. So the more strong the magnetic field is, the more effective is usually the reconnection process. And in that respect, it also accelerates particles then in a more strong way or in a higher energetic way. So you see that all goes hand in hand, so flares and CMEs. There are exceptions from the rules. So there are confined flares, for example, that do not lead to CMEs. But if we have on an average basis, when we look at profiles, so the dynamic CME evolution in the acceleration is very much related to the hard X-ray profile of a flare. So you see the red and green curve here. And if we look at the soft X-ray flux, so to the more thermal component of the emission, this goes well along with the CME speed profile. So we see that obviously the acceleration of particles and the heating of the plasma is then relating to a certain degree to the kind of closing of the poroidal magnetic field in a very direct way, and in that respect, lifting off the CME and giving or accelerating the CME body itself. So this CME flare feedback relation can also help in kind of finding out when you have a very strong flare, you assume a very strong CME as well. As said, there are exceptions with confined events where you can even have hard X-ray, not hard X-ray, X-ray flares with hard X-ray components, but there is no CME related to that. So those are kind of also things that we need to understand. Certain stages of a CME eruption, just as an example. So this is was one of the first events or the first geoeffective event that happened in the new solar cycle 25. It was a long duration M-class flare, and it was related to a filament that became unstable and then erupted. What we can see here is that we have an opening of the field. I will also have a movie later on that. An opening of the field. We see here is already ahead or above the limb, we see some signatures of compressed plasma, presumably. We see darker features here that relate to depletion of density, so usually either waves or dimmings, as they are called. And in white light, we can see how these surface structures then relate to the to the off-limb remote sensing image data. So what we can also do is, for example, reconstructing these three-dimensional objects as they then kind of get lifted off into interplanetary space. So again, we have here the surface structures that then relate to a certain kind of density enhancement in interplanetary space, and this is the CME. So we have filament eruption flares, waves on the surface that then kind of have the pendant or the counterpart in white light there. If we have a look at it, how that looks in the dynamics. So this is from SDO. Actually, instruments, so SDO AIA, an instrument that was built at Lockheed Martin. We see here how the surface structures kind of change very quickly as the flare occurs. These are so-called post-eruptive arcades, and so this is the same event as shown earlier, and the CME is then observed in white lights further out. So maybe again, so we see the kind of change in the surface structures. So we already see here that this is related to the lift of the filament. We see here that loops get stretched, and in that respect, the stretching and the expansion of the CME itself. So here it finally erupts. It causes then dimmings or depletion regions because a lot of plasma is then swept away on the side. And also already here we see that there is either a compression, and this will later be seen then in the white light. And these are the post-eruptive arcades that show then later on. What we observe in white light itself are kind of loops, stretched loops, flux ropes, There is a core that is usually observed, which is presumably or most of the time related to filament material itself. So a cooler plasma material that kind of sits in this flux rope at the bottom part of the flux rope. What we also know is they are optically thin, and this makes a lot of troubles because as they are optically thin objects, they look different from different perspectives. Because it's like a cloud in the sky. You cannot really kind of catch the entire three-dimensionality from one perspective only. And we also integrate intensity over the line of sight. So CMEs appear very different due to the different orientations. This is not the same event looked from stereoscopic perspective. So these are two different events, just to add that. But here we see very nicely these overlying loops or leading edge of the CME, the core of the CME. Here we have this low intensity due to the high magnetic pressure, the flux rope part of the CME. So this is a CME that went off the sun side at the side, so at the limb of the sun. When we observe another CME that started at the center of the sun, so basically this CME propagates towards the observer or even away. This can also be quite tricky to disentangle. We see here this ring type of structure that goes all along the way, which is related, or it's thought to be the shock part of the CME. Where the core actually is hard to define. So this is presumably the core or the CME body. Here we already see this streamer type of things. This is the compressed corona simply because the shock is kind of pushing those structures. So due to projection effects, we might not see the same structures. And kind of relating then for a seamless kind of investigation from the surface to interplanetary space, if we connect an EUV part to white light part, we also need to take into account that we have different information. So there's white light data and density information in the coronagraph images here, and in the surface, as shown before in the EUV part, these SDO movies, these give us usually density and temperature information. So things that appear bright can also be very hot. And basically here we only have the intensity is relating only to the density. So also here we need to be careful about the interpretation. So projection effects could be studied the first time with so very important mission with a stereo mission. So these are two identical spacecraft that were launched end of 2006. Stereo A, both spacecraft completed in the meantime a full 360-degree orbit in 1 AU distance range, so same as Earth or similar, so a little bit further ahead and further inwards. But unfortunately, Stereo B, the connection was lost in 2014. So we get at the moment from Stereo A still a bit of a stereoscopic view, but unfortunately, Stereo B is lost. What we gained during that mission was very important because due to this multi-spacecraft observation, we could learn about projection effects. And here we see how a CME, so that has a shock component and looked from a different side. And when we do some reconstructions, it was found that the shock is a sphere. So it kind of envelopes the entire sun. And so these so-called also halo CMEs, because it envelopes the entire sun, they are observed from any perspective. So wherever you see a kind of a CME that has a strong shock, this spherical type of halo, if it's strong enough, can be observed also from different perspectives because of this huge sphere that is kind of evolving ahead of the CME body. This is usually a three-dimensional sphere that causes a lot of turbulence due to the compression, the turbulence in magnetic field density, etc. And this is usually related to the surface wave that we see on the surface of the sun and usually in EUV. So the driver part itself, so the CME itself is kind of related or is usually simulated by this croissant type of magnetic structure that is more flow from the in situ perspective, so related to a strong, smooth, and rotating magnetic field, because it's this flux rope type that is kind of inherited in that structure. And this we can observe, for example, from the coronal dimmings on the surface. And you see that there are many papers on the kind of geometry of CMEs and how these kind of generate so different types of CMEs or strong shocks are then related usually also to intense geomagnetic storms. As said, new mission or very prominent one is Parker Solar Probe, launched in 2018. Related, so when we relate back to the stereo mission, the three-dimensional or this multi-spacecraft perspective and 3D reconstructions was the kind of the thing that we could learn. And for that, we focused mainly on the outer shell of the CME, so this global structure. What we see now with Parker Solar Probe and the instrument WISPER, so the white light instrument, again, so white light density information is we see many more fine-scale structures in comparison to 1 AU distances. So Parker Solar Probe, maybe I should mention that if you're not familiar, Parker Solar Probe is covering different distance ranges. So it has an orbit that goes very close to the sun, and so in the next years, it is expected to reach below or to come below 10 solar radii. It already reached, I think, 14 solar radii. And in that respect, so the closeness to the sun and the closeness also to this ejector or the CMEs themselves, it obviously gives us a lot of new, a new view, a fine scale, a detailed view with a lot of fine scale structures. And so what we have learned from the stereo era, end of 2006, and 10, 12 years plus, Parker Solar Probe gives us now a very complementary view into the internal part of these structures. And so we see, for example, this driver that I had, so when we jump back a little bit, so the driver part here is now, when you view it from a closer distance, you see much more fine structures. Again, we see this more circular type or spherical type things, but we see that these are kind of twisted inside. We see a lot of blobs occurring here, so small scale plasma blobs. There are many times we see a loop in a loop, as it is called in the meantime, and so the internal core maybe of this structure. So there is not a real consensus on that yet, but people are really on it to find out more about these loop-like structures and these kind of twisted parts and different sizes of these loops. And also rays, and there are many papers in the past few years that were intensively working on these fine scale structures. Just would like to show you one of these. So you can download all the encounter summaries. So encounter means one orbit of Parker Solar Probe. So every encounter you get quick look images where you can observe the structures. We see a lot of dust that hits the cameras. But what we see are a lot of fine scale structures, so things that we have not observed yet in the past, and with that, this becomes a very new and hot topic to investigate. Maybe also to point out here, you see the sun, so getting smaller and also getting larger again. And the time range is usually several days or a week or two. But we see in that also how fastly the spacecraft is changing its distance. So we see that within a few days at the perihelion, the spacecraft is coming very close and then passing by and basically then kind of going away from the sun. And in that respect, we need also to adapt our interpretations because we change the line of sight integration path of these structures. And so sometimes we also do not see these global structures that we are used to observe at 1AU. Also, this is up on discussion. So whether Parker Solar Probe is inside this shock part, which is also interesting to think about, or whether the line of sight, the integration path is so much or needs so much more intensity or density in interplanetary space to become visible at all. So very intriguing new data that we have here. A PhD student currently, so Greta Capello, is working on relating these small-scale structures that we started to observe now to the global appearance. So where actually are these located? And so she identified, for example, for an event. So that was part of this encounter summary that I showed in the previous slide. Identified an event which had very nice twisted structures, as you can see. She identified so-called J-shaped structures and C-shaped structures, and she did a very thorough kind of triangulation on each of these structures. Since Parker Solar Probe is moving fastly, it can also serve as a single instrument triangulation method. So that means Parker Solar Probe observes the structure from different angles over time, and in that respect, you can also do a triangulation just using a single spacecraft, and not necessarily you need to have several or two spacecraft at least. So we see these different structures that she identified, and she derived the location, the speed of these structures, and could kind of group them also in families or different classes or types of structures. We had, so first of all, so there were these twisted structures, as you can see them. Then we have these 3 and the 4, which are so-called thread-type structures, so like a fish bone we observed, and a lot of these fine-scale structures that at a certain angle with relation to that fish bone. And there were also blobs in the aftermath of the CME. And when doing the triangulation and also using the GCS reconstruction, so the global reconstruction of the structure of the CME, so the global view, and combining that with the appearance, the local appearance of these fine-scale structures, she came to the conclusion that these threads and also these twisted structures, they are observed in the legs of the CME. So within that flux drop structure, obviously. In that respect, so this was not of a surprise because we usually, so in our thinking, the 3 dimensions or these parts of the CME, a twisted structure is part of the internal structure of the CME. What we found also very interesting is that these, so there were blob-like structures, these fine-scale structures that I showed you also in the movie before. So a lot of blobs that were occurring in the aftermath of the CME that are usually related to the current sheets and current sheet instabilities in the rear part of the CME. However, they were not kind of centered in this aftermath part of the CME, but were more related to the flanks, so that outside of the flanks. So that means either we have, and they were not grouped. So you see that these other structures, they were kind of clustered together, whereas these blob-like structures, they were distributed in longitude. So that either means that we have a 3-dimensional structure of the current sheet, similar when you think back to the 2D version of the flare-CME relation and how that looks like in 3D. Also, the current sheets that we usually thought of as a array type of thing might be actually a kind of a planar geometry. And in that respect, there might be different locations along which these instabilities occur. Another possibility is also that the solar wind interacts with these flanks, so that we are in kind of the interaction part where the solar wind is basically again where the solar wind regime basically is interacting with the rear part of the CME, because this global structure attached to the sun is also an idealized kind of picture. So this could be the kind of the instability process that occurs as the solar wind starts to disconnect the flanks or the legs of the CME. So those are all very new insights and very interesting, and we will definitely need to do more studies on those things. When we look on CME structures ahead of the CME, so how they interact with the solar wind, it's also kind of intriguing to see how the characteristics of the solar wind upstream of the CME, so ahead of the shock part, is nicely relating to the sheath part itself. So when we consider, so there is the driver, so this global croissant type of shape, we plow through the solar wind. And the interaction, or basically this having a larger speed in comparison to the ambient flow of the solar wind, kind of generates waves or a wave. And this wave ahead compresses the solar wind. And finding that the sheath density, for example, is related to the pre-event speed, so the speed in the solar wind ahead of it, and also the pre-event density shows some relation. In comparison to the magnetic ejector, that shows not really a relation with respect to the upstream solar wind conditions. So we kind of can see that the region, the sheath, forms and consists of accumulated interplanetary solar wind material. And the amount of accumulated mass, or how to form the shock sheath region, depends then also on the background solar wind, on the density and on the flow speed, but also on the CME size, so how that expands in the end. And basically studying then shock and sheath, so this upstream or the kind of structures ahead of the CME, and studying the upstream characteristics, we learn about the CME itself. So we see that this solar wind interaction, and so how that interacts with the object that moves through, is also very still not fully solved issue. And the drawback here is that again we have in situ measurements at only a handful of locations in interplanetary space. The rest is covered by models, and the models are usually they have an inaccuracy, so they are not kind of giving very precise values, and that makes also then these type of statistics rather tricky. When we already talk about structures and in situ measurements, so we saw now a lot of image information, and the thing now is also to relate these white light images to the in situ measurements. So in principle also, what do we actually observe in situ? Again, not only from the white light data to have global view white light data and kind of fine structure detailed white light data to compare remote sensing to remote sensing in different resolutions, but here also to compare a global view coming from remote sensing image data to local variations coming from in situ measurements. And kind of showing the details that we do not derive from this white light data. As said, we had very ambiguous information, for example, for this projected, this halo type of CME, where is the shock, where is the core. For in situ measurements, at least in nice events, you get a more clear view where things are and which type of structures we observe. So typically, so here is the sheath part, the leading edge part, then the magnetic ejector region where the density also can fall below the quiet solar wind. And so this is the density information that we can actually then compare or connect to white light data, because that's the information that we derive from white light data. Then we have, in addition, a very valuable or most important magnetic field information that also gives us information about the BZ components, so the component that couples then, if southward oriented, to the magnetic field of Earth, and that causes then strong geomagnetic effects. So we see that the sheath and the leading edge is connected or related to very highly fluctuating magnetic field, while then in the magnetic ejector, so we have a very smooth, and see also a rotation of certain parts or components, vector components of the magnetic field. The speed itself is, we now have a shock increased here, together again, sheath and leading edge, and then we have a very nice linearly decreasing speed profile for the magnetic ejector part or the flux rope part that is due to the further expansion of these structures. What we actually observe, and sometimes this is also a kind of a crux for forecasts, if we track structures and try to relate them to or simulate them for and validating them with in situ measurements, we need to be very clear what we actually track. As said, sometimes we observe the shock very nicely, sometimes maybe not. So it could be a misleading thing what we actually track and what we model or forecast, because when we track the shock in white light and follow that over time and do some forecasts and relate that basically to the incoming magnetic ejector part, there might be, on an average 12 hours difference. So we see that tracking kind of structures and not relating the same structures to each other can easily end up in uncertainties of simulations of 10 to 12 hours, which we usually have. So the magnetic ejector part, or this bright leading edge, is also usually also very well observed. So this is always a bit a tricky kind of situation. And in principle, if these white light structures that we observe here, so presumably there might be the shock parts that we observe here. So that should be the white light component. And here, that's the shock part behind the sheath, the highly fluctuating. So that's the sheath part. Then there comes this leading edge, which presumably is this very bright and rim type of thing. Where we are also not sure what exactly that is, but it could be a bit of a, or it is most likely a different kind of, has a different physical nature in comparison to the expanding magnetic ejector part. And so the magnetic ejector or the flux rope part in the end here. So there is still a question mark. And I also think we need to have further investigations and discussions about how to relate this remote sensing image information or the data and information that we derive out of that to these very local kind of in situ measurements. And again, Parker Solar Probe and having these fine scale structures is hopefully giving us then in the near future also more insight when more studies are coming in. As already said, and maybe so this is also advertisement of a paper by Volker Bodmer and myself, is the sheath parts is a very interesting kind of structure. It is related to the solar wind, so the characteristics of the solar wind at this specific location. So it also could be used for probing the background solar wind structures. It has also kind of points on a statistical basis where it should become observable better, where it dominates then over the magnetic ejector density and also the magnetic ejector density, where it falls below the ambient solar wind density, is a point that tells us more about the expansion of this structure. So this is a statistical study using back in time, so in the 70s and 80s Helios data, and combining them also with Parker Solar Probe data, and simply back extrapolating these structures to the solar or near sun. And we see that we have several crossings or intersections here, I said, where the different density structures either start to dominate or become weaker again. So recent observations by Tarek Salman reported that these sheaths, they are not observed below 0.38 AU. So somebody's drawing on that slide.
Yes, I think that was by mistake.
Once again, sorry?
I think somebody drew on the slide by mistake.
By mistake, all right.
Yes.
It's gone again. Right, so the how the magnetic fields, so the expansion closer to the sun and the sheath formation, or how it interacts with the solar wind, is definitely at this 0.38 or 0.304 AU distance range a very interesting topic. And I will also come back to that a little bit later in terms of stream interaction regions, so where slow and fast solar wind streams interact. Another just recently published statistics together with Carlos Lavodea. So he went on and not only used Helios and a few Parker Solar Probe data, as I did together with Volker, but he went on and collected all the catalogs that are out there. Is it from Helkatz, from Christian Möstl, from Teresa Nils Chinchilla, Richardson Kane list, so catalogs that are out there and catalogs that kind of give start and end times of shock sheath structures and magnetic ejector parts or flux rope parts. So he collected more than 2,000 CMEs and analyzed those, covering a huge time range, so also more than 2 solar cycles. Distance ranges from 0 to 5 to 5.4 AU, so also covering Ulysses, and doing some statistics. So if you're interested in the catalog, it's freely available, and so please visit the paper and download the data to play by yourself. Carlos also extracted a lot of upstream information already, so there is density, magnetic field fluctuations, so standard deviation of these parameters, all available and extracted to do some more statistics. What we found in these statistics is that the how the CME expands, it changes in its behavior, going from the inner heliosphere to the outer heliosphere. And especially in between these two distance ranges that covers 0.5 to 0.75 or 0.474 AU, and the next kind of distance range, 7.5 to close to 1 AU. So there is a huge increase in the size of the ejector or the flux rope, and that also relates to the so at this distance range, obviously there is a different expansion behavior of the CME. When we go to the outer heliosphere, there are no sheaths, for example, reported. So we have here different categories of CMEs to add here. So CMEs that drive a sheath and those that do not drive a sheath. So we have different expansion behaviors between those. The expansion behavior changes, especially when we go then to the outer heliosphere. However, we have a low data sample, so there needs to be a bit of a caution with those results. But the sheath region, so what's the CME kind of accumulates ahead of it or compresses locally ahead of it, might also influence the expansion behavior of the CME itself. Whether this is due to or related to draping, for example, this is another story, but it could be when we view on the different puzzle pieces, this all nicely kind of can be, or this nicely adds up. So the draping can be studied with non-radial flows and also be related to CME propagation, and in that respect also to expansion of the CME. So there are studies by Carmen Martinic, so a PhD student in the group of Matija Dumbovic in Zagreb, that showed that we have low inclination events, so those are lying in the ecliptic, and high inclination events out of the ecliptic. They have different types of non-radial flows, and with different directed flows in the sheath. So that means in the sheath, definitely we have the draping that is ongoing and the pileup or accumulation of plasma. And obviously the different ejector, the orientations of these flux ropes, they have effects on the expansion. So this is maybe similar as what we have simply inferred from the sheath. So not going into detail with non-radial flows, but just how the sheath behaves and how the CME expansion behaves, having a sheath or not a sheath. So in that respect, draping, sheath buildup or sheath characteristics and expansion characteristics of CMEs, they kind of give us, there is information in there that basically maybe also relates then to the propagation behavior of the CME itself, because draping of field means we add magnetic tension, and in that respect, we might have different kind of propagation behavior. However, in the transit time, there was up to now no drag or no different kind of differences were found. So the differently oriented fields or CMEs together with the field draping and non-radial flows, up to now we could not find strong differences, but this is studies that are ongoing. So basically also asking how the sheath region might affect the CME expansion behavior and how that relates to the magnetic field draping and also to acceleration or deceleration of CMEs and drag itself. That the interplanetary magnetic field has a lot of effects, we know. So there is also reconnection ongoing in interplanetary space, maybe not as effectively, I mean, surely not as effectively as on the sun. So not like accelerating particles, but there are erosion processes or injection processes reported due to the reconnection. So whenever the interplanetary magnetic field has a differently oriented, is differently oriented in comparison to the flux rope, there might be some opening of the field. So we might kind of erode and kind of peel off the flux rope structure. And in that respect, the magnetic pressure decreases, the mass increases, the drag force varies and has a lot of effects on that. So this is a work by Sanchita Pal and colleagues. How the field line orientation and the flux rope, how they interact with each other, and might then kind of lead to a lot of effects like direction change, deflection. So that all then also relates to change in plasma and thermal properties. So in principle, to fully understand the propagation of the CME itself, also the spatial distribution of the solar wind parameters needs to be known, and most of all, or most important of all, the magnetic field itself. So coming now as a last part to the ambient solar wind flow. As said, we have high-speed solar wind flows that are coming out of coronal holes and shape the heliosphere, and that interact with a slow solar wind, and that creates the so-called stream interaction regions, SIRs, and CMEs propagate in that structured solar wind. So that means they interact with these SIRs, and also the sheath region itself might be comparable to maybe the interaction or these SIRs, the buildup of these SIRs. This is how an SIR looks in detail. Also a very nice example. We have a stream interface with an increase in density, the high-speed stream that can be nicely seen in the speed profile, and overall a very fluctuating magnetic field. So in comparison to the CME, a very fluctuating part. That the open solar flux, so how the structure relates to the coronal hole areas, is another story. So we are not kind of sure. So coronal holes are the predominant part of high-speed solar wind streams. However, there are many, or there might be other contributions which are not fully solved yet. But definitely we know that this open flux, so the open field, it shapes the solar wind and interplanetary space. We also know that there is a so-called missing open flux. So we have a discrepancy of a factor of 2 in interplanetary space, so measured in situ, and a comparison to the surface structures. And in all that, the conclusion is the background solar wind models, they lack accuracy because we do not understand yet where open flux comes from and how these structures then the solar wind. And there are important validation efforts ongoing from Martin Reis in an ISWAT team. Another PhD student of mine is kind of looking more into detail about the stream interaction regions, so where fast and slow solar wind stream meets and how they relate to each other, because the compression region there is a comparable process as the CME sheath compression. So we can learn again from SIRs to get more information about CME sheath and vice versa. So what you see here is for the so-called smiley face event in October 22. The PSB measurements of that PSB was at around 0.7875 AU. And we see that this is a purely inelastic collision, so momentum conservation that you see here in the lower panel, in the bottom panel, that is basically using the measurements and transporting them outwards. So we see that the profile is pretty matching, so very nice results here. But still in detail, we see that we are, so that the real observation is kind of is delayed or is coming later. So the steepening in this inelastic collision process is much too strong. So we know that there is momentum conservation that plays an important role in the SIR generation. However, there are also on the obviously more kinetic part of the plasma interactions, there are also other processes that kind of lead to the differences in the profile. So evolution of compression regions using not only CMEs but also SIRs is something that is relevant. Space weather research in the end to use the results that we have here and transfer this into forecasts, and also to kind of give more information on how solar activity shapes our interplanetary space and has effects on Earth and other planets. Maybe as a few messages, the lower the starting height, as said, more effective reconnection is related to strong magnetic fields. So the lower the starting height of CMEs, the more strong the CMEs are and the more geo-effective. On the other hand, we also have CMEs that start very high up, so-called stealth CMEs, that are usually not well observed because there are no surface structures, and also might be kind of having only weak signatures in white light. So those are so-called problem storms because nobody observed them and nobody kind of simulated them. And on the other hand, we have, as already spoken about, the confined events. Information that can give us a kind of additional kind of support towards having confined or eruptive events comes from radio. So type 3 radio bursts could give us some hints towards that. Sequences of X-class flares, so the last that we observed and very well documented space weather event from cycle 24 were the September events, the sequence of X-class flares. And here you see again the surface structures, flares, waves, the CME body, shock wave, SCPs. And yeah, I do not have results yet on the recent kind of sequence of X-class flares that led to the very strong geomagnetic storm just a week ago. But I'm pretty sure at the Space Weather Week in November, we will have a bit more insight on that. But what we can learn and see is that if we have multiple CMEs, so sequences of eruptive events connected to very strong flares, usually these form very complex ejecta and make most strong geomagnetic effects. But due to their complexity, they are also a challenge for all the models. In that respect, we need to improve models and predictions. So we also need and take into account preconditioning effects and interaction of these structures. When doing modeling input for space weather models, we need to kind of also go into the past and have a look what what was going on before, because all that shapes interplanetary space and changes the conditions in interplanetary space. So we need to also look into the past to be able to kind of forecast the present situation, let's say it that way. Yeah, because also of preconditioning effects that last. So if a CME sweeps over Earth, it's usually 2 to 5 days disturbed. So interplanetary space is disturbed and needs to recover from these disturbances. Yeah, the caveats that we have is will be hopefully published soon in the COSPA Space Weather roadmap paper. Just a few short kind of introductions or insights to the impacted Earth. So all this cascade of effects, it changes magnetosphere conditions, ionosphere, thermosphere conditions in that respect. So it has a lot of consequences for modern life, especially communication, navigation, satellites that might experience a stronger drag and might kind of deorbit power grids that are vulnerable in that respect. What we also know is that we have differences in the magnetospheric responses between the CME body or the flux rope part and the sheath region. So these local compression regions have different effects in comparison to the flux rope. Yeah, we also worked recently on relating CMEs and SIRs to satellite drag. So thermospheric density increase is another important ingredient in this kind of coupling process. You all, I guess, heard of the Starlink events in 2022. That was also part of COSPA Athens, a hot topic that led to the deorbit of Starlink satellites. In the meantime, we also learned that there were technical difficulties for those events. So it's not a pure solar storm related event. But nevertheless, we see that when the BZ variation occurs very strongly, very strong southward field, there is an increase in the thermospheric density that goes along. But we also see that there is a delay. And in that respect, we can also give forecasts and warnings for satellite operators when in situ actually a BZ component is measured. And for that, we developed, together with the Technical University of Graz, the so-called SODA tool that currently runs under ESA. And last but not least, interdisciplinary projects like magnetosheath jets that I mentioned in the very early, in this setting up the scene slide. There are structures that are generated inside the magnetosheath, the so-called jets. These blob type of things, they might impact on the magnetopause and then also cause diffuse aurorae and space weather effects. So there are reported events on that. So we also do not fully understand these coupling processes. And there seems to be a connection. And I also would like to highlight and advertise the Heliophysics in Europe, the first workshop that will take place in ESTEC in November this year. And yeah, coming to the summary, I hope I could show you and also explain how the different structures or signatures that we observe are usually starting from the sun with very in energetic processes. Magnetic reconnection is the key and is the common ground of all these brightenings, ejectors, and acceleration processes. The ambient magnetic field configuration, how high or how low the CME occurs, how strong overlying magnetic fields are, it controls the CME onset and also the expansion behavior. Coronal holes are giving us information on the ambient solar wind structures, high-speed solar wind streams that also kind of have a strong influence on the propagation. They also can interact with these CMEs. They precondition interplanetary space and then causes a change in the CME dynamics itself. So for that, we need all the models kind of need to be validated also in order to improve the performance. So combining data in situ and image data in different resolutions is also urgently needed, not only to understand what we observe and what we track, but also to feed the models with a higher accuracy. Yeah, the cascade of reactions that we have at planets, especially at Earth, is not fully understood. So space weather is not only about forecasting, it's about science. Since we are not there yet, there needs to be a lot of more science that needs to be done on that to better understand those cascades. And in that respect, this is all a highly interdisciplinary research field and needs international teams and cross-disciplinary kind of expertise. And again, I would like to highlight the heliophysics workshop and heliophysics in Europe. And I hope that science teams will kind of form out of that to bring us more insights and to better understand the physics behind those things. And with that, I thank you very much. And I'm open for questions.
Thank you very much. It was a very dense but very informative talk.
Sorry, a bit over time, yeah.
No, so I think there will be questions. Yes, Professor Douglas, would you like to coordinate the discussion?
Yes, of course. I can coordinate the discussion. So anybody? You have provided a lot of information.
Yeah, basically you get everything collected.
Everything, yeah.